Okay.
Just a sec. Let me see if it runs. Okay. Okay, we are live and it's 4 p.m. at least here in Warsaw. So welcome everyone to our next Warsaw Astronomical Observatory Tuesday seminar series. And today we continue on our exploration of the planetary studies topic. And today we have a guest from Ohio State University, Professor Scott Gaudi, who did his PhD also there. And he also was has been always a good friend of the Ogle team and Ogle people, and many people have worked with him in Ohio. So it's been a long-term collaboration with Scott on the topic of microlensing. However, Scott is not only a microlenser, he also does transiting planets. He's an expert in exoplanets in various areas, and he has been involved in the space telescope, which used to be called W1. Now it's called Roman, as I've been told, Nancy Grace Roman Space Telescope. And we are going to learn about this telescope in the exoplanet search with this telescope from Scott. Scott, please.
Okay, thank you. I assume everyone can hear me and see my slides. I want to thank you for the invitation to come and give this virtual colloquium. I want to apologize in advance for my complete inability to pronounce most Russian names, as Rada can attest to. So when I butcher a Polish name, please forgive me. So I am indeed going to be talking about Roman, but in particular, I'm going to be talking about the Roman Galactic Exoplanet Survey. So this is what was formerly known as the W1 Microlensing Survey. And I want to shout out to Matthew Penny, who's a faculty member at Louisiana State University, previously a postdoc working with me, and Samson Johnson, who's a graduate student working with me. And I'm going to be presenting some of their results on what we can expect from Roman regarding the Galactic Exoplanet Survey. Okay, so a little bit of motivation here. Before 1995, or at least this is what we tell our undergraduate students, this was the only planetary system that we knew of and that around a star. And of course, this is our own planetary system. I've done some revisionist history here and removed Pluto, which was a planet at the time. And if you think about the structure of our planet, our solar system, it's actually kind of interesting and not what maybe you would expect if you were tasked to design a solar system. In particular, we have 4 glorified balls of rock sitting relatively close to the sun. The largest and most massive planet, which is mostly hydrogen and helium, is sitting kind of smack dab in the middle. And then as you go further out, you get sort of more or less decreasing mass monotonically, but ever increasing spacing from the sun. So the challenge given this planetary system, solar system that we have, is how did it form? And so given one data point and a lot of time to think about it, we came up with a pretty good story for why our solar system looks the way it does. And the basic idea goes like this. And first, if you believe that planets form from the bottom up, which most people do for at least most planets, then if you think about what's required and planets form in protoplanetary disks, you have to understand the physical processes by which micron-sized dust grains, which condensate out of the protoplanetary disk, grow by something like 13 or 14 orders of magnitude in size and 38 and 41 orders of magnitude in mass to get to the present day masses and sizes that we see for mature planets. And so you can imagine, as you cross all those orders of magnitude in mass and radius, the dominant physics that governs the growth of the planets is going to change dramatically. And so you have to understand physical processes all the way down from the micron size level to things that are the size of Jupiter and the Earth. And so, as you can imagine, that's hard. And so it's, a common phrase in exoplanets is planets are hard. But nevertheless, like I said, given a lot of time to think about it, we came up with a pretty good model for to explain why our solar system looks the way it does. And I'm just going to briefly go over it. I'm not going to do justice to this model. Again, the basic presumption is that planets form in a protoplanetary disk. So you have a giant molecular cloud, and part of that molecular cloud is basically unstable under its own self-gravity. So it collapses. When it collapses, it has to conserve angular momentum. So although some material ends up in the center, most of the material ends up in a protoplanetary disk that's very flat and very hot. As the disk cools, particles begin to condense out of the disk. These particles are roughly the size of microns. These particles come together first by van der Waals forces, and then by some process we don't completely understand, eventually accrete to the size where they can begin to attract each other gravitationally, and then they grow up to be planets. And so that explains why all the planets in our solar system are more or less in a disk. Now, to understand why we have this two populations of rocky planets and gas and ice giants in the outer solar system, we have to understand what kind of building blocks we have to form planets. So this is my cartoon of a cross-section of a protoplanetary disk. So when you're close to the protoplanet, to the protostar, as the grains condense out, if you're very close to the star, the protoplanetary disk is very hot. And so you can't get any grains condensing out. Eventually, it's cool enough that you start to get very high temperature refractories like iron and nickel. As you get further out, you get things like silicates, magnesium, silicon, oxygen forming rocks. And then eventually, once you get to a magical place that was about 2.7 AU in our solar system, you get cold enough, roughly 150 Kelvin in a vacuum, where water ice can condense out from vapor form. And so that's called the snow line. And because the two most dominant, two most abundant elements that actually like to combine with other elements are hydrogen and oxygen, that means that your surface density of solid material, once you cross beyond the snow line, jumps by a factor of several. So you have a lot more material to build planets, and so you can build planets faster and you can build bigger planets. So in the outer solar system, the way we think it proceeded is that you rapidly accreted. So this shows mass here as a function of Earth masses, as a function of time in 10 million years. So the solid line is the rocky core, and the sort of dashed dot line is the envelope. So you first accrete a rocky core quite quickly until basically you've grabbed all the solid material within your gravitational grasp. And that's roughly about 10 Earth masses for the location of Jupiter and what we think the mass of our protoplanetary disk was. And then you're kind of stuck. You can slowly accrete gas, but that gas has to cool. And so you can only accrete gas on a Kelvin-Helmholtz timescale. And so that you enter a protracted phase where you slowly accrete gas, it cools, you can accrete more gas. But eventually you build up an envelope that's massive enough that it's as massive as the core, at which point the whole system is dominated by the mass of the gas. And so then you can have a genes-like instability and you get runaway gas growth up to something like a gas giant and like Jupiter and Saturn. And so we would think of Neptune and Uranus as something like failed gas giants that never actually reached that critical core envelope mass that was equal to the core mass, where you get runaway accretion. And in particular, if you because this phase is very protracted, if the disk disappears anytime during this phase, you're going to end up with failed Jupiters. And it's only the ones that actually form quickly in gases and disks that last a long time that are going to form gas giants. So you have slow growth and then this critical core mass and then runaway gas accretion. Now in the inner part of the solar system, you have a very different situation. In this case, your what's called isolation mass, where you basically grabbed all the mass in your gravitational reach, is much smaller. It's roughly the size of Mars or even less. And so you have a lot of relatively small protoplanets and they stick around and slowly accrete. And eventually they sort of accrete in lockstep and grow slowly. And they do that. And then eventually when the gas disk goes away, The eccentricities and inclinations of these protoplanets, which are called oligarchs, are damped down by the residual small particles or small protoplanets that are around, but eventually they grow massive enough that they're more massive than that background sea of smaller particles, at which point they begin to notice each other. They begin to pump each other's eccentricities and inclinations. They undergo orbit crossings, giant impacts, and eventually merge to form a few terrestrial planets like we see in our solar system. And so that model explains the rocky planets in the interior. And because you start off with much less solid material, you never reach a mass where you can accrete a substantial envelope of gas and hydrogen and helium. So that basic model explains the structure of our solar system, why we have rocky, relatively diminutive planets in the inner part of the solar system, and then gas and ice giants in the outer part beyond the snow line. So that's all well and good. And this model matched the data well. We only get one data point. But we all know what happened next. In 1995, the first planetary companion to a sun-like star, not really, but that's what we say, was discovered around 51 Peg. And contrary to our expectations, where giant planets we thought only could form beyond the snow line, which is at large separations, again, about roughly 3 AU in the solar system, 51 Peg B was a gas giant located about 10 stellar radii from its parent star, with a period of about 5 days, and had a mass of roughly half that of Jupiter. So likely a gas giant, but exactly where a gas giant shouldn't be according to this fairy tale that I just told you about. So that immediately indicated that planet formation was more complicated than we thought. We still think that giant planets form beyond the snow line, most likely, but then they have to somehow migrate into the close separations that we see for these hot Jupiters, of which 51 Peg was a prototype. So the bottom line is we figured out that planet formation isn't just hard, it's really hard. And where there's additional physics that was missing in this simple model that I explained. So one I've already mentioned is migration. But we also have to consider that if we're looking for planets around other stars, the host star may be different and the metallicity of the star may be different. So that might change planet formation as well. We think that large-scale dynamical interactions are relatively common in planetary systems. If you have planets very close to the stars, you have to think about tides. Disk properties may be different, and there's completely different models of planet formation. So how can we possibly hope to really understand planet formation? Well, the basic thesis of this work is that all that physics, that rich physics that happens as planets grow by these many orders of magnitude, must be imprinted on the final distribution of planet parameters. And there's some pretty well-known examples of this. One, because you have this protracted phase of slow growth for giant planets, you expect there to be a desert between planets of roughly that of Neptune and that of Jupiter, which is sort of what we see in the solar system. There's no planets with mass intermediate to those two. We expect giant planets to be rare around low mass stars because the planet formation timescale is longer and you have less material. We also expect free-floating planets because of dynamical interactions can eject planets from their natal planetary systems. And so the idea is that if we can measure the distribution function of planets, the number of planets is a function of whatever physical parameter, mass, period, semi-major axis you can measure, then you can look for these features in the distribution, which will give you clues about the planet formation physics. And so the goal is to determine the demographics of planets, or a complete census of planets, statistical census over broader region and parameter space as possible. So this is where we are now with the current status of exoplanets. This is a little bit old, but not too bad. So this shows, these plots are sort of required to show in any exoplanet talk. This is planet mass as a function of period, planet radius as a function of period for the known exoplanets. And the planets are color-coded by their detection techniques. So blue here is ground-based transit surveys. Black here is radial velocity surveys. And then we have microlensing here shown in cyan, and some direct imaging planets here in the upper right. And then the planet radius period diagram, you can see this very large population of planets discovered by Kepler by the transit method, most of which actually don't have masses, as you can see on the left here. There's lots of interesting features to note. One is that you can see that most of the radial velocity planets are detected relatively far out at separations of a few AU, and they're giant planets, gas giant planets. Most of them don't have radii, for example. But the most noticeable thing is this paucity of planets in the lower right corner of both of these plots. And this is partially covered by planets discovered by microlensing, but not entirely, and I'll talk more about that. And so, and the reason for this, of course, is just selection effects. But what's interesting is that the planets in our solar system mainly occupy this region of parameter space that is not being explored by most current methods. Okay, so that means that we're likely missing out on a very large population of planets, both from our expectations from theory and from what we know about the solar system. And so that hampers our ability to try to understand planet formation because of the incompleteness of this statistical census. So these are the methods we have at our disposal for detecting exoplanets. We have radial velocity, which we're all familiar with, transits, direct imaging, and microlensing. Each of these methods, and then a bunch of other methods, which I won't go into, each of these methods has their own biases and planets that they're most sensitive to. Radial velocity and transits are most sensitive to massive close planets or large close planets. Direct imaging is mostly sensitive to young, relatively high mass planets at very large separations, much greater than 10 AU. But microlensing actually is sensitive to planets that have separations that are intermediate between what's probed by radial velocity and transits and direct imaging, and can probe planets in that semi-major axis regime down to very low masses, as I'll talk about. So I'll talk about, this is going to be a relatively brief primer on microlensing, because I think this is a fairly well-informed crowd for the most part in terms of microlensing. But nevertheless, it's not familiar to everyone, so let me go through it relatively quickly. So this is the basic. This is actually data from the OGLE collaboration of the first microlensing planetary event that was discovered by the OGLE and MOA collaborations. You can see the stars here in the galactic bulge, and most of them are constant flux, but you can see this one here, nicely highlighted by a circle, is changing in flux. This is due to a microlensing event. And in particular, it has several times when it has very sharp increases in flux, which is the signature of a planet. So everything I'm going to talk about here, I wanted to show this first just to remind you that this actually happens. It actually happens a lot. And we've detected many planets, even though it's going to, for some people that are not familiar with it, it's going to sound like kind of a crazy detection method. So the basic idea is relatively simple. If you stare at a star in the galactic bulge, now we're typically talking about, for long enough, eventually another foreground star is going to pass relatively close being within 1 milliarc second of that background star. When that happens, the foreground star is going to bend the light from the background star that would have missed us into our line of sight. And so we see a displaced image of this background source. Now, if we now look at it, so that was a side view. If we now look at it from our perspective, if the lens, which is shown here in the black dot, and the source in the red circle are perfectly aligned, then the lens is going to image the source into a ring, which is called the Einstein Ring. And it's given by this combination of the mass of the lens and the distances of the lens to the lens and the source, and relative distance between the lens and the source. And the Einstein Ring has a radius that's typically about 1 milliarc second for a typical lens mass of a half solar mass, located about halfway between the distance from here to the galactic bulge at 8 kiloparsecs. Now, typically you don't have perfect alignment, and when you don't, you have two images. One image that's called the major image that's outside the Einstein ring, another image that's inside the Einstein ring. When the source is inside the Einstein ring, these two images are very close to the Einstein ring, and their separations are roughly twice the Einstein ring radius. That's, again, a few milliarc seconds too small to be resolved, although it has actually been resolved in, I think, 2 cases now, using the VLT gravity instrument. But in general, you can't resolve them. But what you can measure is the magnification of this background source, which is just given by the area of these two images divided by the unlensed area of the source. And so this is a static picture, but of course the lens, the source, and us are all moving in the density field of the galaxy. And so what you have here is, here I'm fixing the lens to be in the origin just for convenience. You can see the background source passing close to that lens. You can see the two images being formed, and you can watch as the images grow and shrink in magnification, in size, and therefore in magnification. And so what you end up getting is a time symmetric microlensing event. And the time scale is roughly the time scaled across the Einstein ring radius. And so that's theta E divided by the proper motion. And that's about 25 days for a typical event, but it can range from, because the proper motions can range from roughly 1 to 15 milliarc seconds per year, and the Einstein ring radius can range from 0.2 to 0.1 to 2 milliarc seconds. You get time scales of roughly a few days to hundreds of days. The trick with microlensing is that it's stochastic. You can't predict microlensing events ahead of time. So that means that when I said you have to watch one star for long enough here means typically about 500,000 years, which is pretty long for a typical graduate student lifetime. So instead of watching one star for 500,000 years, we watch tens of millions or hundreds of millions of stars. And then we know, and then at any given time, several of those stars are being gravitationally microlensed. And then another thing to note is that because you're just measuring this time scale for most events, it's a degenerate combination of the mass, distance to the lens, distance to the source, and relative lens source proper motion. So the time scale alone does not actually give you the mass of the lens or its distance. Okay, what does this have to do with planets? Well, if this foreground lens, again, the foreground star, happens to have a planet, and that planet happens to be in the path of one of these images, then the gravity of that planet is going to perturb the light from that image. And what you're going to get is a deviation on top of your microlensing event. And that's the signature that you've detected a planet. And you can see that blip right here. And the time scale of that perturbation is roughly the crossing time of the planetary Einstein ring. So that goes as the square root of the mass ratio times the primary time scale. But that's about 1 day for Jupiter mass planet, a few hours for an Earth mass planet. Now, because these images are largest when they're closest to the Einstein ring, which is when the event is magnified, you have your highest efficiency for planets near the Einstein ring. High magnification events give you higher detection efficiencies. So typical peak sensitivities are around 3 AU for a half solar mass lens. And if you scale this with respect to the expected location of the snow line in the protoplanetary disk, you get a relatively weak scaling with the mass of the host star, which means in general, microlensing is sensitive to planets. Most sensitive to planets are roughly twice the distance of the snow line from their parent stars, nearly independent of the mass of the host. And so that makes microlensing complementary to other detection techniques. Now, because microlensing is sensitive directly to the planet mass and it works by perturbing images, it doesn't require light from the lens or the planet. As a result, it's sensitive to planetary systems throughout the galaxy, anywhere from here to our line of sight to the galactic bulge, or 1 to 8 kiloparsecs. You can detect planets if they're close to the Einstein ring radius, that's the peak sensitivity. You can detect planets out here if they're far away from the Einstein ring radius, if they happen to just be along the path of the source. But you can't detect planets that are very close to the star because those are perturbing very demagnified images. So you're sensitive to wide and to planets beyond the snow line out to very large separations. And of course, you're in principle even sensitive to free-floating planets, because a free-floating planet would just act as a microlens by itself, albeit would give rise to much shorter timescales. So the planets that you're really not sensitive to are the short period or small separation planets. So yes, yes, no. Okay, so this is probably a familiar figure to many people, one of the most exciting results to come out in microlensing recently. As I mentioned, microlensing is sensitive to free-floating planets, and that's just because they act as isolated lenses. They have shorter timescales. Ultimately, the magnification is limited by the angular size of the source, which I'll talk about here in a second. And so to detect these things, you have to have very high cadence and relatively good photometry, but you can detect them. And this is a classic, this is already a classic paper, I would say, by Pshemek, led by Pshemek with and the OGLE collaboration, as well as the KMTNet collaboration, indicating the probable detection of a free-floating terrestrial mass planet. So there's many papers that talk about detecting free-floating planets with microlensing. And this would be very interesting because we think planet ejection is a generic byproduct of planet formation. And so the total number and mass function of free-floating planets is almost directly related to the physical processes of dynamical interactions in the formation of planetary systems. So it's a key probe of planet formation. I mentioned that the magnitude of the signal is independent of the planet mass. Obviously, that must be only true to a limit, because you can't have a dust grain giving you infinite magnification. So where this approximation breaks down, all right, so I'm showing that here. I have a planet where I'm just start off with a large mass ratio and slowly shrink it. And you can see that while the deviation decreases in duration, it doesn't really decrease in magnitude. And again, for Earth mass ratio planets, you get a deviation that's about 2 hours. So the duration decreases, and also your probability of detecting the planet decreases, because the smaller the planetary Einstein ring radius, the closer it has to be aligned to the image to get a significant magnification. So the detection probability is a few percent, and it scales roughly as the square root of the mass ratio of the planet. Okay, so signal magnitude is independent of planet mass ratio, but the signals get rarer and briefer. Of course, the limit here is when the angular size of the Einstein ring radius of the planet is smaller than the angular size of the source. And then you're only magnifying a small part of the source. And so your magnification gets suppressed. And that's shown here in this theoretical paper by Bennett and Ree, showing the magnification due to an Earthmass planet, the perturbation for a main sequence lens, subgiant, giant, and asymptotic giant source, sorry. And you can see the larger the source, the more suppressed you get and spread out of the deviation. So where this starts to become important, again, is where the Einstein ring radius of the planet is equal to the angular radius of the source star. And that turns out to be roughly the mass ratio of the Earth to the host star for a solar type star in the galactic center. And so below that, you can still detect planets, but again, the perturbation starts to be suppressed. So detecting low mass planets requires 1, monitoring main sequence stars, 2, having very high cadence, and 3, having relatively good photometry. In terms of the mass function of the host stars, basically anything that has that is a condensed object along your line of sight to the background source can act as a lens. Any of those things might host lenses, host planets. So we're sensitive to planets orbiting main sequence stars, brown dwarfs, and even remnants like white dwarfs, neutron stars, and black holes, should they host planetary systems. Most of the hosts we expect to be relatively faint. Okay, so this is sort of the unique benefits of microlensing. You're detecting planets beyond the snow line, the very complementary to other techniques. You're sensitive to very low mass planets. You're sensitive to long period and free floating planets. You're sensitive to planets orbiting a wide array of host masses and host mass types, stars, brown dwarfs, and remnants. And you're sensitive to planets all along your line of sight. So you can, in principle, determine the galactocentric distribution of exoplanets, and in particular, determine whether or not planets are more common or rarer in the galactic bulge, which is a very different stellar population than the galactic disk. Okay, so microlensing events, microlensing surveys have been going on for a long time, as we all know. And those surveys have actually been searching for planets or helping the search for planets since basically even before I started graduate school in 1995, but really got into the swing of things around then. And so we didn't detect the first planet around with microlensing until 2003. But since then, we've detected almost 100 planets with microlensing, over 100 planets now with microlensing, many of which were led by the Ogle collaboration, I should note. So what have we learned from this population of planets? Well, one of the first things we learned is even from the first 4 detections, first 2 of which were sort of giant planets, gas giant planets, we predict. And the other 2 were actually low mass cold planets, super Earths or maybe Neptune-like planets. And given that the sensitivity to those lower mass planets is much lower, as I discussed, the fact that we found 2 giant planets and then 2 smaller planets means that there must be many more small planets than large planets. So this was the first major result to come out from microlensing surveys. This is, now a very classic detection led by the Planet collaboration, but also with data contributed by Ogle, MOA, and Robonet, showing this very small duration and small amplitude perturbation due to a planet that's roughly 5 times the mass of the Earth, but with a separation beyond the snow line. And this is actually, I think, the lowest mass planet detected at the time. And again, was evidence that these cold, low mass planets were actually quite common, or at least much more common than Jupiter mass planets beyond the snow line. Now, with the larger samples that we have, we're able to do a statistical analysis of all the planet detections. So the most comprehensive and recent one that's been done is by the MOA collaboration. This is Suzuki et al. There's been other papers before and some since then, but I would say this is sort of the state of the art. And this is a busy plot, but let me just draw your eye to a few results. The main result here is in this gray shaded region, and this is a broken power law fit to the distribution of planets discovered by the MOA collaboration based on, I can't remember how many years worth of data, maybe 10 years. And they find a very sharply falling mass ratio function as you go to higher masses. But then they find a break at around Neptune mass, and then either a flattening or a decrease in the planet frequency below Neptune mass. And that's being here compared to the frequency of planets discovered by radial velocities here. This is the Cumming et al. Result, well known. So this is giant planets located at smaller separations. These are also results from various radial velocity surveys for giant planets around low mass stars. And these are some results for radial velocity surveys for low mass planets around solar type stars. And so so again, you see that there's this very sharply dropping mass function. Now, what's interesting is that if you compare the frequency of giant planets, which here I'm saying is something like mass ratios of greater than 3 times 10 to the minus 4, microlensing surveys indicate that these planets can be quite common, but radial velocity surveys around low mass stars, or radial velocity surveys find that they're quite uncommon, at least at higher masses and smaller separations. And the reason for this is just because the mass ratio function is a very steep function of mass ratio for large separations. Okay, slides are not advancing. So this is also showing now the results from that MOA survey in gray here, and now being compared to ab initio planet formation models. This is exactly what we set out to do, is to compare our models to our data to see if we can learn something about those models and the planet formation processes. And so the red shows the histogram, the gray is the parametric fit to the MOA data. You can see that, and then the blue and different colors of blue here and blue and yellow here are these ab initio models by two different groups. One is Ida and Lin, and the other is the Byrne group. And what you can basically see is that even if you mess with the models of migration or change the mass of the host, you really can't fit this very relatively smooth power law that is seen by MOA and other collaborations. In particular, you typically get a paucity of planets between mass ratios of roughly that of Neptune and something like Saturn. And this is that prediction from this slow growth phase of giant planet formation, where either you basically get stuck in the slow growth phase and only have a mass of roughly that of Neptune, or you run away to a giant planet, but you don't get anything in between, because that's a very rapid formation phase where you accrete from roughly 20 Earth masses to 100 Earth masses. And so it's very unlikely that you get stuck in that very short phase of the evolution. But that paucity is just generally not seen in microlensing. And it's an open question as to why it is. It means that this core accretion scenario for giant planet formation is likely more complicated than we thought. Okay, so that's kind of a very brief overview of just some of the exciting results that have come out of microlensing surveys for exoplanets. But I want to get on to the Roman contribution from Roman. So let me go back to this plot. Here again in cyan are showing the planets detected by microlensing. And again, we have quite a nice sample, 100 planets. They are starting to fill out this region of parameter space. But I think it's fair to say that we're kind of hitting the limit of what we can do from the ground. Even the most advanced surveys, OGLE, MOA, and in particular KMTNet, are really just struggling to find Earth mass planets. They're finding them, but it's hard. And it's hard to build up a lot of statistics on these low mass planets. And getting below an Earth mass is going to be really hard from the ground. Maybe we'll get some lucky and get a high magnification event with a small source star. And the other thing to notice is that ground-based microlensing surveys are really only sensitive to relatively narrow range of separation, despite the fact that I told you they should be sensitive to things even out here like the ice giant analogs, although there are a couple ice giant analogs, I should point out, one of which was found in a paper led by Roddick. But it's going to be tough sledding to broaden this parameter space a lot from the ground. So if we really want a complete statistical census, we're going to have to go to space. So just to show you in perspective, this is a plan view of our solar system where I've included Pluto for my own uses here. And this red dot is the region of sensitivity of, so these orbits of Jupiter, Saturn, Uranus, Neptune, and Pluto. This is the region of sensitivity of the Kepler survey, which is the largest statistical survey that we have on hand that's detected that many thousands of planets. So blowing that up, basically you're only sensitive with Kepler to planets out to the radius of roughly that of the Earth. So a very small fraction of the area of the solar system. So we really need to try to complete the census. It's going to be difficult to do from the ground. And the reason why we want to do this is there's a variety of theoretical reasons. Again, we still think most giant planets form beyond the snow line. We would like to place our solar system in the context of other exoplanetary systems. We know that we're pretty sure that planets that have formed in the habitable zone likely formed without water, because the habitable zone is interior to the snow line. So that means water that we have on Earth had to be delivered from the outer parts of the solar system, and that likely required planets outside the solar system. So in order to understand habitability, and water delivery and habitability, we have to understand the properties of the outer solar system. And we'd like to understand the frequency of planets in different environments. So those are all well and good theoretical motivations. But if we've learned anything in exoplanets is that if you're guided purely by theory, you're likely to be led astray. So the real reason why we want to complete the census is basically what we learned from 51 PEG, which is basically to expect the unexpected. We should just probe regions of parameter space that are open to us or become open to us because we never know what we're going to find. And our theories are often proven to be wrong or incomplete. In other words, Mother Nature is more imaginative than we are. So how do we go to Earth mass and below with microlensing? Well, again, you have to monitor hundreds of millions of bulge main sequence stars on a time scale of 10 minutes. You have to get relatively good photometry of a few percent. Again, you have to resolve out the main sequence stars to get that good photometry. If you want to get masses of the host stars, you actually have to resolve out the background stars so you can detect the host light, which gives you a handle on the mass of the host star. So as shown by Bennett and Reed, argued by Bennett and Reed originally, this basically means you have to go to space. And the reason why is shown here. On the left are simulated images of what W first would see for a crowded region in the bulge. And the right is the same scene, but now seen from the ground with seeing limited observatories. And you can see that every one of these stars, things that looks like a star, this is just a blow up, looks like a star, say here, looks like one star, is actually an agglomeration, an asterism of many stars. And the main sequence stars, which you can see here in the space-based image, are essentially invisible. The things you see here are either agglomerations of unrelated stars or giants. And these are not particularly suitable for detecting Earth mass planets. So if we want to detect Earth mass planets and below, we have to go to, first we'd like to go to the infrared so we can peer through the dust to more crowded regions, which gives us more sources, more microlensing events, more sources and lenses and microlensing events. But therefore we have to go to more extincted fields. So it's good to go to the infrared. We also want to be able to resolve the main sequence stars as shown here in the space-based image. That allows us to look for planetary deviations around low magnification events. And again, as I mentioned, isolate light from the lens star. In space, you can get nearly complete coverage of the bulge, at least at certain times of the year. Of course, you can't do that from the ground, except in Antarctica, and there the conditions aren't very good, and that's only for some amount of time in the bulge season. And of course, we expect from the space to get to have better systematics because we have a more well-behaved point spread function in our data. So that allows better characterization of the planetary anomalies and more robust quantification of sensitivities. So the science enabled by going into the space is that you get sub-Earth mass planets, you can detect even potentially habitable zone planets, free-floating Earth mass planets, and you can get even mass measurements. So that brings us to Roman. So Roman is named after Nancy Grace Roman, who was the first female administrator in NASA and the first NASA chief scientist. She's also often called the mother of Hubble. The Roman Space Telescope is named after her, and it's Roman for short. What is Roman? Well, it was the #1 recommendation for a large space-based mission in the 2010 US Decadal Survey. It was a notional mission based on taking several different ideas and putting them into one mission. One was a JDM Omega, which was a dark energy mission. The other one was the Microlensing Planet Finder led by Dave Bennett, which is basically a space-based microlensing satellite. And then the Near Infrared Sky Survey, which is led by Dan Stern. What the Decadal Survey noticed was that the hardware requirements for these three missions were very, very similar, and particularly need large field of view with near infrared. So they said, hey, why don't we invent a mission that can do all three of these? And so that's what they did. They originally called it W first. And it was to have a dark energy survey component, an exoplanet microlensing survey, and then also a guest observer program, including a galactic plane survey. So that was the origins. Since the origins, Roman has gone through many designs, and I have been there since the 2010 when this all started. So NASA put together some teams to come up with design reference missions. The initial science definition team came up with two mission types, a 1.3 meter and a 1.1 meter version. But then in roughly 2012, I believe, it was announced that NASA had been gifted 2 space-qualified telescopes that were 2.4 meters in diameter. They were donated by a NASA government agency, which we are not allowed to say what the agency is. But if you'd like to know, all you have to do is Google this. And NASA decided that they would repurpose one of these telescopes for what was then WFIRST. And I will say that we were told when we were given these telescopes that we could do anything with them except point them down at the Earth. So if you want to know what these telescopes were originally used for, that's a clue. Because of the larger aperture and also because of the new laws, that we also considered a coronagraph instrument that would block starlight to detect faint companions around nearby stars, and to actually make this telescope serviceable, even though it's going to be at L2. Okay, so that kind of gave WFIRST a shot in the arm. And the current version of WFIRST design, now Roman, is a 2.8 meter effective aperture. It has a wide for space area set of detectors, which has an area of roughly 0.3 square degrees. It has wavelength sensitivity from 0.5 to 2 microns. The full width half max is roughly diffraction limited at 0.1 arc seconds. It's undersampled. The pixel sample size is 0.11 arc seconds. The life to launch is supposed to be in 2005. That's probably going to slip to 2006 at least. Lifetime is nominally 5 years, but likely can go for longer. And as I mentioned, it's going to be in L2. The main instrument is the wide field instrument. It has 18 H4RG detectors, so that's 288 megapixels. This field of view is around 100 times the field of view of the largest instruments on Hubble or JWST. It also has 7 filters and then also the chronograph, which I won't really have time to talk about. So these are the filters for those of you that may be interested in things other than microlensing. It has, again, filters from 0.5 to 2 microns. We've actually added another filter here, which isn't shown in this image, a K filter, K short filter. And there's also a wide microlensing filter, which is shown here in the gray, that spans 1 to 2 microns. That's so we could collect as many photons as possible. And then there's a grism and a prism as well. This shows sort of the layout of the focal plane, the wide field instrument, as compared to the area of several instruments on HST and one on JWST. So you can see the area is much, much larger. It's small compared to, of course, the area of the Ogle 4 cameras, but it's large compared to any space-based telescope at this resolution. All right, let me move on. Okay, so a lot of people wonder, is this actually going to happen? WFIRST, now Roman, has had a very checkered history. It's been on and off. It's been quite a roller coaster ride. But, and I used to say yes, parentheses, maybe. I decided to take out the maybe because I think Roman's actually going to happen now. I have a fairly high confidence level that this is going to happen. For one thing, we had a new start in February 18, 2016. That means NASA said, yay, verily, this is a real mission. They selected science investigation team proposals from proposals that were due on October 2015, and the teams were announced in late 2015. I was lucky enough to be a PI of one of these proposals that was selected. It's been canceled now 3 times in the president's budget, but each 3 times it was restored by Congress. So we're now back to being restored. Who knows what will happen in the next fiscal year, but there are rumors that it's not going to get canceled again. Anyway, the project is now in what's called phase C in NASA speak, but what that effectively means is that they're actually putting hardware together. They're actually soldering wires together. So it's now a real thing. In fact, the primary mirror is already reground, polished, and has been resurfaced. And so we're really actually building this thing as we speak. We now have 20 flight ready detectors of the 18 that we need. This is this Roman Galactic Exoplanet Survey science team that I'm the PI of. Dave Bennett is the deputy PI. You can see we've actually accreted a large fraction of all of the microlensers in the world and several non-microlensers as well. And this list is probably incomplete. I tried to update it last night, but it might be incomplete. You might see some familiar names here. I want to highlight in particular Samson Johnson and Matthew Penny, whose results I'm going to be showing here right now. So this is a great team of very talented people, and it's been very fun working with them in helping to build up the science survey strategy and science case for the Roman Galactic Exoplanet Survey. So these are the nominal parameters of the survey. This is likely to change based on community input, which we're going to be seeking actively between now and launch. But nominally, it's a 2 square degrees area of the bulge that's going to be monitored. That's roughly 6 fields, or 7 fields, I think. And we're going to have 6 seasons, each of which is 72 days, centered on the equinoxes. We're going to get about 40,000 exposures per field in the wide filter, with a cadence of about 15 minutes during the seasons. We expect about 1% precision at ABW149. That's the wide filter magnitude of 21.5. We'll get down to a 23rd magnitude in that filter, roughly 10 to the 8 stars we'll be monitoring. Okay, so here are the notional fields, all 7 of them. The number 7 is basically set by the slew and settle time. I screwed up my animations here. This is based on simulations done by Matthew Penny, again, who's a previous postdoc, now a faculty member at LSU. You can see the extinction map and the placement of the current optimal placement of the fields as best we can estimate. So what Matthew does is he simulates a scene in the galactic bulge. You can see here, you can see these beautiful diffraction spikes and airy rings in this simulated image. And then he injects microlensing events in these simulated images. And some of those have planetary perturbations, which then are detectable. So this is the signal of a planetary perturbation, as you can see from Roman. And you can see this is one 72-day season, and then hidden behind Matthew here is another 72-day season. This particular event is a perturbation due to a planet with a mass of twice the mass of the moon, or roughly the mass of Ganymede, at a separation of roughly that of Jupiter, around a host star that's around 0.3 solar masses. The delta chi-squared here is 710, so that's about 27 sigma. So these are not subtle detections, even for extremely low mass lenses. I want to briefly go into free-floating planets. This is a story I think is probably pretty well known to most of you, certainly to some of you. Way back in 2011, Sumi et al., on behalf of the Mo and Ogle collaborations, announced, so this plot shows a distribution of the number of events as a function of their Einstein timescale. And you can see that most of the distribution can be explained by main sequence stars, white dwarfs, remnants, and brown dwarfs, but they found an excess of short timescale events at small timescales, or excess of short timescale events, which they interpreted as due to a population of free-floating planetary mass objects, and that implied a frequency of such objects of roughly 2 per star in the galaxy, which was a very surprising result. That result stuck around for a while until 2017, when Pshemik did similar analysis, but for a larger data set with Ogle only. Also found a distribution of timescales that's very similar to that of what the Mo and Ogle found, but did not find this excess of short timescale events at 1 day. So this suggested that excess was spurious, and it was likely due to systematic errors in the photometry. Interestingly, what Pshemik and the Ogle collaboration did find was an excess of very short timescale events, which would correspond to Earthmass planets if these were real. Now, they weren't very well sampled, And so they were very tentative about saying that these were real excess, but nevertheless, they argued that they could be microlensing events, and that would imply one free-floating Earth mass planet per star. Since then, we've detected, I think, 5 or 6. OGLE KMTNet collaborations have detected 5 or 6 much more well-characterized short timescale events that are consistent with Neptune down to Jupiter down to Earth mass free-floating planets. And these are very likely to be microlensing events, indicating that this excess here may very well be real, but we need more data to find out. From Roman, we can detect Earth free-floating planets actually quite easily because of the high cadence and high photometric precision, especially for main sequence stars. So this is showing simulated microlensing light curves from free-floating planets. This is work done by my graduate student Samson Johnson for different planet masses. This is a brown dwarf. This is a 2 Jupiter mass free-floating planet. You can see it's very well sampled. This is a Mars mass free-floating planet. And this is a 0.6 mass Earth mass free-floating planet, but transiting a giant source. So you can see you get these extreme finite source effects. And this event here looks very similar to the one I showed before, the actual detected event by Shemek et al. By the OGLE and KMTNet collaborations. So this is what we expect from Roman. If you look at the expected yields, we don't really know, of course, because we don't know what the mass function of free-floating planets is. But if you adopt the mass function that's consistent with bound planets from microlensing, you find that you'd expect this distribution in the gray histogram of planets detected as a free-floating planets detected as a function of time scale. So you get this main body due to stellar and brown dwarf and remnant lenses, but then you get this tail due to free-floating planets. And I'll just highlight this part right here, which is the if that excess of short timescale events by the OGLE collaboration is real, this is what that would look like in Roman. So you would easily detect many of those events, and we could confirm that excess is real or not. If we don't detect anything, which I think is unlikely, we can put very firm upper limits on the total amount of mass that is ejected per star in planetary system free-floating planets as a function of the mass of the planet. That's shown in the solid line. I think this is the 3 sigma limit. And so to read this, if we detect no 1 Earth mass free-floating planets, that means that we can show that at most 0.1 Earth masses of 1 Earth mass free-floating planets are ejected per star, or 1 per 10 stars. We can put that upper limit on the number of free-floating Earth mass planets. And then this is these here are various other limits from ground-based microlensing surveys like Macho and Eros, Kepler surveys, a Subaru survey. You can see these are order of magnitude less constraining than what Roman will be. This is the original result by Sumi, which again was shown to be spurious. This is the result by Shemek. And you can see here, this is the tentative excess of Earth mass planets. We could detect that easily with Roman by several orders of magnitude. This is the upper limit that the OGLE placed on Jupiter mass free-floating planets. Again, we can improve that by orders of magnitude. And these other lines are showing various theoretical predictions for what the mass function of free-floating planets might look like. And you can see we're sensitive to many of these theoretical predictions. So Roman is going to put very strong constraints on the total mass of free-floating planets and their mass function. I'll just briefly mention, because I'm running out of time, that Roman will actually be, perhaps surprisingly, because I said Roman's not sensitive to very close-in planets, which planets in the habitable zone generally are, but because it's looking at so many events and has such an exquisite photometric sensitivity and is looking at main sequence sources, it does actually have some sensitivity to terrestrial planets in the habitable zone. So this gray region here shows the estimated habitable zone as a function of semi-major axis and planet mass. These black dots, just focus on the big black dots. Those are planets detected in a simulation orbiting host stars of greater than half a solar mass. And you can see that we can get we expect a handful of detections in or proximate to the likely habitable zone. And that's very similar to the number of detections found by Kepler. So it's a small number of detections, but we can extrapolate from the detections of larger and more massive planets, larger separation and more massive planets into the habitable zone to get an estimate of the frequency of potentially habitable planets, also called A to Earth. And we can compare that to Kepler. And ultimately, if we find agreement, we can combine the two to get a better estimate. And that estimate of A to Earth is very important for future potential direct imaging planets to look for and try to characterize Earth-mass planets orbiting nearby sun-like stars. Okay, so this is again the parameter space probe by Kepler. Matthew has estimated the parameter space probe by W first, and it looks like this, or sorry, Roman, and it looks like this. So you can see we cover nearly all the parameter space occupied by the planets in our solar system. And of course, we can detect free-floating planets as well. So to sum it up, this is the what I like to call the penny plot, because it was made by Matthew Penny, and it's very striking. This shows, again, planet mass and semi-major axis. The black dots are planets already known, detected by various methods. The red dots are planets detected by Kepler. This red line is Kepler's sensitivity limit from its main survey. You can see it just barely missed the Earth mass planets, or terrestrial habitable zone planets, which is why only had a few candidate detections. And then this blue line shows this predicted sensitivity of W first. This line is where if every star had a planet of a given mass and semi-major axis, you detect 3 of them. And you can see that it extends all the way down here to about 0.02 Earth masses. So these are the planets here. Here's Mercury, Earth, Venus, Mars, Jupiter, Saturn, Uranus, and Neptune. You can see that W first would be sensitive to analogs to all of these except for Mercury, but who really cares about Mercury? And would even be sensitive to large moon mass planets, either isolated or orbiting their host stars. So together with Roman and Kepler, you get a complete sensitive exoplanets from 0 to infinity, separations from 0 to infinity, and masses greater than that of the Earth, including habitable zone planets, free-floating planets, the galactic distribution of planets, lunar mass satellites, and you get about 100,000 transiting planets for free. I'm going to skip this, and I'm just going to put up my summary slides. The basic takeaway message is that with Roman combined with Kepler, we can finally get a relatively complete statistical census of exoplanets and to determine exoplanet demographics, which will be important for testing planet formation theories. And with that, I'll take questions.
Right. All right. Thank you very much, Scott. I'll do the clapping on behalf of everyone. Virtual clapping. So are there questions to Scott? If you have a question, then please raise your hand on Zoom so that I can see it and let you speak. And while people are thinking about questions, I will just comment that the animations, the GIF animations, Scott has shown, he is the only person in the world who is allowed to show them, actually. But everyone is using them everywhere. So you actually seen the actual author of those animations. They are extremely popular. I think you've made them something like 20 years ago, right?
Yeah, I was a postdoc when I made them. I never thought they were going to be used that much, but yeah, they're used all the time.
Well, they're great. They just show the essence, and and funny thing about GIF files. If you made them into some animation format, we would probably not be able to read them, while GIFs are still readable. So
yeah, I remember when I was making them, I'm like, I'm totally wasting my time doing this, but I guess I was wrong.
There are no citations, unfortunately, connected.
No, there are no citations. But people usually reference me, so.
Great. There is a question from Marius, please.
So, hello, Scott.
Hi.
So actually summarizing your presentation, in the beginning on the slide you show that today until now, it is majority of detected exoplanet, it is by transit method, yes?
Yes.
Yes. But microlensing, it looks very promising. Yes.
Yes.
So do you predict that in the future, in the nearest future, we're using this microlensing, or let's say this microlensing, this can dominate in the planetary research? Or in other words, it is, do you predict that amount of detected new exoplanet will be larger than using microlensing, will be larger than using other methods?
Yeah, so that's a great question. The real answer is we don't know. So if I go back here, here's these blue dots are simulated detections from Matthew based on his simulations, assuming a mass function that's consistent with what we know from the mass function of cold planets from microlensing surveys from the ground, but extrapolated to much smaller planet separations and much smaller planet masses and a wider range of planet separations. So a lot of this is basically made up. And of course, that's the case because if we knew what these planet distributions look like, we wouldn't bother doing the survey. So the prediction is that we'd find about 1,400 bound planets, which would not be more than Kepler. However, that prediction is based on a wild extrapolation that's almost certainly wrong. And it could very well be that very low mass planets are much more common than even Neptune mass planets. In particular, these very low mass objects like Ganymede could be the embryos of giant planet formation, which might mean that they're very, very common in some planetary systems. So it could very well be that we actually end up detecting more planets than with Kepler, but our baseline prediction is a factor of something like 3 less than what Kepler sees, but still a lot, enough to do very good statistical analysis.
Okay, thank you.
I have to ask this. You didn't mention astrometry at all.
No, I did not. I didn't have time, but thank you for prompting me. So one of the great things about Roman is that you have one very high angular resolution, and hopefully you have very stable point spread function, and you can characterize your detector very well, and you have a lot of reference stars, which means you should be able to do relative photometry. So in individual measurements, we predict you should be able to, for a sort of typical source star where we get 1% photometry, you should be able to get astrometry to about a milliarc second. If you're actually able to beat that down by the square root of the total number of measurements, which is 40,000 per star, you can actually get down to statistical precisions of a few microarc seconds, which would allow you to detect, in principle, parallax of bulge stars, which is really exciting, and astrometric microlensing, which is probably what you're getting at, exactly. Which would allow you to detect. So astrometric microlensing is the fact that you have the two images that are unresolved, but they have different and varying magnifications, which means that as the microlensing event happens, the centroid of the source moves, and the amount it moves is proportional to the angular Einstein ring radius. So with that measurement, which has been made now in a few events, I think, not very many. I think we're going to expect more with Gaia, and there's some. Obviously, you led a paper on a very exciting Gaia event on that. I guess we're waiting to see if there's astrometric data on it. I'm not sure. But anyway, with this, you can measure. In principle, you can measure. Combine this with other measurements like the annular parallax to actually measure masses. It's going to be hard for main sequence stars because we have to really have very good control of systematics. Might be possible, we're not sure. But certainly for more massive lenses like stellar remnants, you can do this quite easily. And so one of the exciting sort of byproducts of our Roman Galactic Exoplanet survey is being able to measure the mass function of isolated black holes. And we expect to detect 100 or several hundred isolated stellar mass black holes with this survey.
Excellent.
Great question.
Looking forward to this. Any other questions to Scott? I have a natural question. What happened to the other mirror which was there? You don't
We
know.
do not know.
But you know it
They were
exists.
thinking about so I have actually seen both of them with my very own eyes.
Wow.
I have a great story about that, but I don't have time to tell it. Let's just say I had to basically leave all of my electronics behind, including my cell phone, before I went into the building, and I had to be escorted everywhere. I couldn't go to the bathroom by myself when I was in this building. Another clue as to what these were originally purposed for. So it exists, but and they were thinking about using it for another NASA mission, maybe a planetary science mission, but it has since kind of disappeared, and no one, at least no one in my pay grade, knows where it is, but obviously someone knows where it is. So
I see. There is a question from Tomek, please.
Hi, so I'm looking in your penny plot, and there are these colored regions there. So I wonder, if do you think that these regions correspond to some physical mechanisms, or these are selection effects on the distribution of planets?
the color regions, you mean the different shaded regions here?
No, I mean the dots that you have over there. They cluster, right?
Yeah. That's purely selection effects. So you're most sensitive to, so we've adopted a mass function that is basically that rises towards lower mass objects and then flattens out. And that mass function, and this is a very interesting and somewhat surprising result. At the high mass end, that mass function is actually measured by ground-based microlensing surveys, and it has almost exactly the same absolute value of the detection efficiency slope as a function of mass ratio, except it's in the opposite sign. So they cancel out. And so the observed distribution is basically flat up until you get to that break where we have assume that below that, the mass function is constant, and then you start losing detections. And again, I said microlensing is most sensitive to planets near the Einstein Ring. That's roughly here. Sensitivity falls off for planets closer and for planets further away. And if you can squint, you can see that it falls off faster for planets closer than for planets further away, as I described before. So this is all just selection effects. If we wanted to get the true distribution of planets, we have to back that out by including the detection efficiency, which is obviously something we're going to be doing for the Roman survey.
Okay, thanks.
No.
Okay. Great. Thank you, Scott, for joining us, for being in Warsaw for a while. Thanks for a great lecture. And we hope to meet you sometime soon in reality. So I'll do the clapping on behalf of everyone. Thanking you for this lecture. And I thank everyone for joining. And we continue the planetary topic over the next semester, over the entire semester in next week on Tuesday. Thank you. Okay. Goodbye.
Thank you.